So I know Monday's lecture is pretty intense. Okay, today we'll have various topics, 4.7, 4.8, 5.1, but they're all pretty straightforward. They're not too bad. Okay, 4.8. Newton's method. You know, Newton and Leibniz were the co-founders of calculus in the West. Makes sense that this is something that's named after him. Although it's kind of ironic because Isaac Newton hated it when people got credit for what he did, and yet this method, in its modern form, actually Thomas Simpson, who we're going to talk about later on, is more responsible for the modern form of Newton's method. Okay, but Simpson has his own method named after him, so we'll deal with him later. Okay, Newton's method. Newton's method. All right. Now, what's the point of Newton's method? All right. Well, what was a key point in pre-calculus? In pre-calculus, what was a key goal? A key goal was to find zeros of a function. Right? Find zeros of a function. Wasn't that something that you often did in pre-calculus? Right? Something like solve f of x equals 0. Right? By the way, folks, when you find the real solutions for f of x equals 0, what do those real solutions, what do the real zeros for this guy correspond to graphically? They correspond to what points on the graph? X-intercepts. Yeah, the real solutions of this, the real zeros for that guy, they basically give us x-intercepts. And, you know, that helps, right, when you're graphing. Okay. Now, why are we talking about this now? Well, for a few reasons. For one thing, we're now talking about setting f prime of x equal to 0. Why? What kinds of numbers do we try to get when we set the derivative equal to 0? The critical numbers, the ends, yeah. Critical numbers, and then we can try to look for local extrema, right? So we're interested in the zeros question. Also, we set the second derivative, f double prime of x equal to 0. That's to get what I call pins, okay? Because we might want to look for what kinds of points, IPs, inflection points. Okay? So that's one reason why we're mentioning this method now, because this issue of finding or approximating zeros, that comes up when you want to find, well, x-intercepts, even in pre-calc, but now critical numbers for local extrema and pins for IPs, inflection points. All right. And there's a second reason. Okay. The second reason is that if you think about this general issue, finding zeros of a function, we're going to use derivatives to accomplish this task. Okay. So back in 2.8, I mentioned the bisection method for approximating zeros. The bisection method for approximating a zero. Okay, there's no guarantee we'll get all of them, but we want to find a zero for the function. Okay, so what were sufficient conditions for there to be a zero? Right. Well, try to look for values x equals a and x equals b. All right, such that the function value was what here and what here.
Positive and negative.
Yeah, positive and negative in either order, right? For example, if the function value is positive here and negative here, or vice versa. And furthermore, if f has what property? Well, it's got to be defined on that closed interval. Oh, continuous. We love continuity, right? Okay. And we also have continuity. F continuous on closed interval. All right. Now, do you agree with that? Well, I hope you do, right? Because this is a consequence of the IVT, the intermediate value theorem. But if f is continuous on the closed interval, and if the function value switches signs from here to here, that means that somewhere in here, we're going to get a zero, an x-intercept. Don't you agree? Okay. And how do we do it? You know, bisect, cut in half. And here, test values, right? What's the function value here? Let's say it's negative. Okay. Cut in half. Let's say it's positive here, right? So you keep chopping, chopping, chopping until you get a zero. But bear in mind, there could be round off there, but until you basically get a zero, or until you get a window that's small enough where you're saying, you know what, we'll just take the midpoint, go home.
With that method, is there a possibility that if you do too large an area, you could skip over a possible area where there's two x-intercepts?
Oh, of course, of course. That's why I said this is meant to approximate a zero.
Okay.
For all I know, there could be,
You're just using it to
well,
find
there could be
one.
infinitely many. If it goes flat there, there could be infinitely many zeros in there. Yeah. But yeah, this is just, now, so these are sufficient conditions for the existence of a zero in each of these search spaces, right? Okay, I notice anything about uniqueness. Yeah. Okay, Now, Newton's method does something similar. It's a similar goal. In a way, it's the same goal. But this time, we're going to use derivatives, and we're going to need differentiability. Okay. So now, in 4.8, now, okay, we're going to use f prime, and we're going to require differentiability. Okay. So how can we use not just continuity, but differentiability to make this search process more efficient? Okay. Because the deal is that even though it's kind of like the first derivative test versus the second derivative test, in the sense that even though there are cases where this fails, where this doesn't help us, okay, still, when it works beautifully. This guy, he's slow, he's like a turtle, right? This guy is slower, but he's more reliable. Okay, so there are more general cases, continuity is more general than differentiability. Provided that you can find these kinds of values for A and B, where you switch signs. But in a sense, this method is more reliable, but it's slower. It's slower. Although granted, our computers are so fast nowadays that, is it a matter of 3 seconds versus 5 seconds, but this method here is not as efficient as Newton's method. All right. So the goal here is to approximate a zero using derivatives, all right? Because, folks, we don't always have exact formulas, all right? Like the quadratic formula, okay? If f of x is quadratic, yeah, you have that quadratic formula. And in fact, for third degree and fourth degree polynomials, we have similar algebraic formulas. They're ugly, but they exist. And actually, mathematicians like Abel, they proved that there's nothing like a quadratic formula for fifth degree, sixth degree, and beyond. Okay, we don't have anything like that quadratic formula for those guys that are algebraic in structure. Right? Or what if I give you some hideous guy? F of x equals, oh my god, e to the 3x sine of x minus tangent cubed, tangent cubed, some mess, right? Okay, we may not have exact methods for finding zeros for that. Okay, we don't have a magic super formula that finds zeros exactly. All right. Okay. By the way, one comment I want to make. So you might be going, well, beyond this, why else might we care? Well, here's the deal. What if you want to solve an equation? A of x equals b of x. Okay, so you have, blah, blah, blah equals blah, blah, blah. All right? Well, you could subtract b of x from both sides. A of x minus b of x equals what? 0. This would be f of x. What's my point here? If you have an alien species that can find zeros exactly for any function, that species can do what? They can solve any equation. All right? So these are equivalent skill sets. Okay? Your ability to solve equations is good up to your ability to find zeros. Right? They're equivalent skills. Okay? Just like the quadratic formula. If you know the quadratic formula, you can find the zeros for all quadratic functions, and you can solve all quadratic equations, right, with real coefficients. Okay. Any questions? That's where we're bothering. We're basically talking about, well, how can you approximate a solution to an equation? Right? If you have to, subtract some junk on one side, isolate 0. But basically, how can you approximate a solution to an equation? All right. Okay, so there's a point to what we're doing here. And to this day, you have software like Mathematica that has variations of Newton's method. All right. So what's the idea here? Okay, the idea of Newton's method. Okay, so we're going to exploit the idea of differentiability here. Okay, in addition to continuity. All right. So here's the idea. X-axis, y-axis. All right. So let's say we have a guy like this. All right. So here's the graph of some function f. So we have y equals f of x. All right. And we're looking for an x-intercept, or a 0 for the function. Here I'm indicating 2. Okay, we like this guy or this guy. I want one of these guys. All right. Now, with the bisection method, okay, you did have to start somewhere. Okay. So one problem with this method is that you do need to find values for a and b where you have a switch in signs. Okay, so you have to start somewhere, right? Okay, and that was one thing that made the bisection method difficult to apply in some cases. Right? Now over here, you have to start with a seed. You have to start with an initial guess. Okay, so that's kind of the price you pay. You have to come up with some guess at first. All right, now so let's say that you guess over here, x and 1. For example, maybe you're playing with a graphing calculator, okay? But you know, the graphing calculator can only go so far, right? Or can only zoom in so closely. But let's say that based on a graphing calculator, you're guessing something like x1. Okay. Now you're really blowing it up though. All right. Now x of 1, that's not a 0, that's not an x-intercept. But we look at its corresponding point up here. All right. By the way, what are the coordinates of this point? It's going to be x of 1, and how do you denote the y coordinate? F of x of 1 is the function value. All right. Remember, you plug into Big Daddy F to get the y coordinate. All right. Now here's the deal. Okay, I want to ski down from this point over to, let's say, this x-intercept, presumably, right? Closer one, this x-intercept. But here's the problem. I might not know that much about f, okay? Because the world is not always f of x equals x squared, right? Maybe f of x is really ugly. Maybe I don't have a closed form for it, right? I just know bits and pieces of information. Like maybe it's from an experiment, right? I'm just taking, I'm watching a bird, I'm taking a stopwatch and taking measurements every 5 seconds. So maybe I don't have a nice closed form for f of x. So in that sense, maybe I can't ski down like this because I don't know enough about this function. But here's the thing. Even though I might not know how to ski down this curvy thing, there are certain graphs that I have a very easy time analyzing. For example, what can we use to approximate the graph, at least around this point? How about the what? And the derivative tells me about what line? The tangent line. Here's the strategy. Okay, we're going to use the tangent line. So instead of skiing down this slope, which we don't know much about, we're going to be skiing down the tangent line. Okay, and we're hoping that the tangent line, hugs this graph pretty well. Okay, at least close by. All right, so let's go ahead and do that. Let's draw the tangent line. Okay, here's the tangent line. Now, just like with the bisection method, this is going to be an iterative algorithm. It's going to go in a loop. All right. Well, what do you think we're going to take as our next guess, x sub 2? We're going to take the what of that tangent line? The x-intercept. Yeah, it makes sense, right? Because you would think that if the tangent line is meant to approximate this white graph, okay, then the x-intercept here should be close to the x-intercept there. That's a hope. Now, that's not always going to be the case, but that's the hope. Okay? This picture is kind of idealized. We're hoping it kind of looks like this. All right. Here's going to be x sub 2. All right. So I'll write this out. Okay, so how does this all work? You start with a seed, an initial guess. Bear in mind, on a test, you won't have to guess. I'll give you the starting point. But there are problems where, for example, there are problems where you can try to approximate pi, and you might want to start with, 3 or 3.1 or something. Okay. Or you want to approximate the square root of 2. Right? You'll probably start with 1.4. Okay, so a seed or initial guess, that's x sub 1. Again, that would be given to you on the test. All right? And what is x sub 2 going to be? Let x sub 2 be the x-intercept of the tangent line to the graph, okay, at x1 f of x1. So x2, our next guess for the x-intercept, for the 0 of the function, or a0 of the function, right, is going to be the x-intercept of this tangent line. All right. Repeat the process. Okay. So we're at x2. We look up in this case. Of course, you could look down sometimes, but here we look up to that point. Okay. And guess what? We draw the tangent line of that. Yeah. We draw this guy's tangent line. Oh wow, this guy's pretty good. This is going to be our x3. So it's an iterative process. X sub 3 is going to be the x-intercept of a tangent line at x sub 2. F of x sub 2. Okay. And you can see that, we're going to converge pretty quickly. Converging means that you're getting closer and closer to the thing that you want. Okay, so this is an idealized situation. It looks pretty good. We're going to get very close to that x-intercept over there. All right, etc. All right. When do we stop? We'll talk about that. Again, we have issues of rounding off and all that. But any questions so far? Do you agree that this is a reasonable scheme? It's a reasonable scheme, all right? However, I must warn you, there are cases where this method fails. It's like the second derivative test. Sometimes it just blows up on you. But we'll talk about that later on. All right. Questions about that? That's the scheme. That's the scheme. But now here's a question you might be asking. So wait a minute. Do I have to find this tangent line, and I got to find this, then find the tangent line? No. We're going to automate the process. Because don't you agree that it would be great if we had a formula, just a single formula, that'll get us from x1 to x2 to x3, without having to, find the new tangent line and da-da-da. You agree it would be better to automate the process, right? A formula. Is there a formula we can get that can get us from x1 to x2 to x3? Well, people like Newton and Simpson, they figured out a way. All right, so let's automate this process. And really, if you know your pre-calc and you know what a derivative is, then it does make a lot of sense. You can derive this. So, issue C. How do we get from from x sub k to x sub k plus 1? For example, from x sub 1 to x sub 2. All right. Okay, how do we perform the iteration? How do we go from one guess to another guess without having to repeat a whole block of steps? All right. How can we automate the process? All right. Well, let's look at this very first tangent line here. All right. And we'll start with the point-slope form for a line. Over here. Okay. So let's start with the point-slope form for that first tangent line. Point-slope form for a line. Y minus y sub 1 equals what? Well, eventually, yeah, but over here.
Slope x.
Slope f. Times the quantity x minus x sub 1. Okay, review lines. 0.14 in pre-calc. Review lines. All right, y minus y sub 1 equals m times the quantity x minus x sub 1. Okay, x sub 1 is our c, our initial guess. Y sub 1 is this guy, right? It's the function value at x sub 1. Okay. All right. So two things I'm going to do here. Two things I'm going to do. All right. Y minus, as I just said, okay, y1 is the function value of x1, right? y1 is f of x1, all right, equals, what is slope in calculus? What's the slope of the tangent line? It's the derivative of f at x1. So what's m? I'll put this in big brackets. What's the slope m? It's f prime at x1. All right, it's the derivative evaluated at our c. Okay, times quantity x minus x sub 1. So this represents that first tangent line. Okay, so this is the first tangent line that we're dealing with. Okay, this is the equation of our first tangent line. You all agree? This is the equation for our first tangent line. And again, I'm assuming differentiability if these derivatives exist. Right? Okay. I mean, of course, if you have a VA or something in here, that could be real trouble, obviously. Or even a corner of a constant. Okay, now, what do we want to do here? We want to find an x-intercept. All right, so we want to find the x-intercept for that tangent line. Find the x-intercept of the line, the tangent line. How do we find an x-intercept? You set what equal to what? What equal to 0? Well, y equal to 0. Okay, so you take this guy, y, you're going to set that equal to 0. All right. So we have 0 minus f of x1 equals f prime at x1 times quantity x minus x1. Right? Of course, the 0 there, we can kill. All right. Now, what we want to do here, we want to solve for x. We want to find the x coordinate that will make this happen. We want to solve for x. All right. We have this right now. So what do I do with this guy? Divide by him. And you better hope that the derivative is not what? 0. Now think about why that's a problem. Why is it a problem if the derivative is 0? What kind of a line has 0 slope? Horizontal. Do you see how that might be a problem? Yeah, you're probably not going to be able to find the x-intercept. We'll talk about that. All right, wait when you divide by him. So you get the opposite of f of x1 over f prime of x1 equals x minus x1. All right? I'm solving for x. What do I do to both sides? Add x1. Correct. x1 minus f of x1 over f prime of x1 equals x. All right? Which means that's how we're going to get x2. So what is this new guy? It's our new guess. That means that x2, our new guess, is going to be, just turning it around, is going to be x1 minus f of x1 over f prime of x1. In general, okay, how do you get x sub k plus 1? Okay, how do you get the next iterate? How do you get x sub k plus 1? You take x sub what? 2. Well, that's 3. X sub k in general, yeah. You're right, that's 2, that's 3. If this is k plus 1, that's k. That's the previous guy, right? It's like a deduction, right? Okay, here's k plus 1, here's k, all right? Minus the function value there over the derivative there. Okay, and this works where k is a positive integer. All right. This, ladies and gentlemen, is the key formula behind Newton's method. Although, if you remember this, I'm not going to ask you to write this verbatim. Okay, it helps, but I'm not going to ask you to write this verbatim. If you can write this down, that's sufficient. Okay, and that's good for portraits, right? Okay. All right. Questions about that? Questions? That's the formula. You don't have to keep drawing the graph or figure out the tangent line. This is an automated process. That'll get you from x1 to x2 to x3 to x4 and so forth. Okay. So what's the way to remember this? Okay. Well, the new guess is the old guess, okay, minus the ratio of f to f prime at the old guess. Okay, that's the way to look at it. The new guess is the old guess minus the ratio of f to f prime at the old guess. Now, a lot of people make a mistake, well, not a lot of people, but you might make a mistake by flipping these. One way to remember that's like this is that we don't want f prime to be 0, right? That's bad. Okay, 0 is bad. Okay, like Frankenstein talk. 0 bad. 0 bad there. What if f is 0? Actually, we're happy. That's what we want. If f is 0, we're done, right? So obviously you're in bad shape if f prime is 0. And you're going to see why. You're going to see why it's bad if f prime is 0. Okay, so that's the way to look at it. All right. We'll do some examples. Any questions? Any questions? All right. Example. Okay. Now this might not seem like a Newton question, but you can phrase it like a Newton question. Approximate the square root of 5 to 4 decimal places. Okay, you can think of this as a Newton question. Right. Now bear in mind, this is not a question that comes up in industry, just get a calculator, right? But let's say that you're on a desert island, and you have a wimpy $2 calculator. It can't even do square roots. It's a basic arithmetic calculator, all right? You can't even do square roots, all right? How can you approximate the square root of 5? And you don't want to do trial and error, okay? Approximate the square root of 5 to 4 decimal places, okay? The square root button is plus under your calculator. You can't take, raise to 1/2 or something. All right. How can we rephrase this? Okay. In other words, that is, approximate, okay, the positive root of f, where f is the following. All right. So here's the deal. Here's the deal. All right. X equals root 5. We're going to go backwards. Normally we end with that, right? But we're going to go backwards. It's like a Jeopardy deal, inverting. Okay. I want to find a function, okay, that has that as a 0 or a root. Okay. Square both sides. X squared equals 5. There's no need to check. It's okay, we're picking up negative root 5. And then, well, how can I rewrite this equation so I get 0 on one side? Subtract 5. X going to let f of x be x squared minus 5. Do you agree that the square root of 5 is the positive root, the positive 0 for that function? With this rule, x squared minus 5, right? X equals root 5 will make that thing 0. We all agree. All right? That's going to be our f of x. So for a problem like this, you actually have to figure out the rule. Okay. Of course, another problem, I give you the rule. All right? And that's the more standard problem. Okay, f of x equals x squared minus 5. We want to find a positive root for this. All right. Okay, now what about our c? X sub 1. Now, on a test, I would give you the c, but come on, just use your common sense, your mathematical sense. The square root of 5 should be close to what? It'll be 2 point something, you think, right? Because the square root of 4 is 2, right? And the square root's increasing. So you think square root of 5 is 2 point something on it, right? Why not try 2? Okay, you can try 2.1. Let's try 2. All right. Let's let our c, x of 1, be 2. Okay. Again, on the test, I will give this. So from here, let's go ahead and use 2. Now bear in mind, 2 is not a 0 for this guy. Okay, so we're not there yet. So let's try using. You agree that the derivative works out nicely here. All right, let's work this out. F of x is x squared minus 5. Therefore, what's this derivative? F prime of x. 2x. Okay, and that's going to be good everywhere. So we have differentiability. Right, there are no VAs or funky things going on. We should be okay. I mean, we have a parabola. Shouldn't be too bad. All right. Before we go on, again, I want to make sure not to forget this. I mentioned here, if you have a situation like this, this is bad, right? What if you get stuck? If you get stuck, what do? You stop, get a new seed. Sometimes you give up and you restart the whole process. All right. All right. Now, in my notes, it's kind of an overkill, but in my notes, I actually used some algebra to get a really nice formula. But I'm worried that that might be too intimidating for some of you. I mean, if you're good at algebra, then go ahead and do it. I hope you are good at algebra, all right? So in my notes, I tried to get a nice, convenient rule in one fraction. But, you know, that's up to you. Okay, I don't want to spend time on that here. So I'm going to go ahead and just do it brute force, and let's just do it the longer way. All right? All right. So what is x sub 2 going to be? All right. X sub 2 equals, all right. So remember how it works. It's the old guess. Well, I just wrote this, right? I didn't have to erase this. It's the old guess minus the ratio of, now what goes on top? Is it f or f prime? It's f. It's the ratio of f to f prime at x1. And remember, we don't want this to be 0. Okay, then the whole thing blows up. All right. Well, let's go do this. X1 is 2 minus, all right. Well, you take 2, you plug it into the big daddy. All right, so it's 2 squared minus 5. Okay. Down there, well, the derivative is easy. Just take twice the daddy. Okay. Twice the daddy. Okay. By the way, folks, either make this a 4 or, remember, this is a double division. I noticed some of you were rounding off on the chapter 3 test wrong because it was something like 10 over 27 pi. And I think some of you did 10 divided by 27 times pi. That's wrong. It's a double division. It's 10 divided by 27 divided by pi. So remember here, this is a double division. You're dividing by 2 twice. Please keep that in mind. All right. I assume you've worked this out. All right. And it says to 4 decimal places. Now some people say you should go to 5, but I'm okay with 4. Okay, some people say you should go to 5. But let's go to 4, and you get... actually, you know what? It's exactly 2.25. Okay, in fact, this is exactly 2.25. And just to indicate that we have that level of accuracy, go ahead and put a couple of trailing zeros. Okay, for now, just to indicate that we do have that level of accuracy. All right, so that's our next guess. Okay, 2.25. By the way, I'm not making the claim that that's necessarily closer to the square root of 5. I'm just saying that's our next guess. Okay, we might just be on the other side. Any questions so far? Any questions? twice 2.25, work that out separately, that's 4.5 down there, okay? When you work this out to 4 decimal places, this is going to be about 2.2361. All right. Questions? Question. You might be asking, well, what question might you be asking? When we stop. Well, guess what? Let's try to do it again. And if you do this again, all right, x sub 4, okay, we'll do the work here. It turns out that when you do x sub 4, you do the work here, all right, guess what? Is it 4 decimal places? It is, 2.2361. When do you stop? Okay, we want this thing good to 4 decimal places. The rule is that if you get 2 consecutive iterates where it's identical to the desired number of decimal places, you stop. That makes sense because what if we do it again? You're just going to keep getting the same thing over and over again, right? Okay, so we can stop here. You stop, okay, when we get 2 consecutive iterates, sk and sk plus 1, that are identical to the desired number of decimal places. Okay, in this case 4, because I said so. But you could go a little bit further. Now actually, just like I said with the second derivative test, okay, Newton's method, when it works, it can work really beautifully and really well. In fact, in numerical analysis, where they deal with these kinds of algorithms, by the way, one of the dirty secrets of applied math, we often don't have exact formulas like the quadratic formula. So we might go just use a computer algorithm, right, where we incorporate something like this, where it might seem like it's not as mathematically sophisticated, but you know what? It gives us an approximation. So a dirty secret in applied math is that we often do have to do approximations. It's not do exact formulas. That's the field of numerical analysis, how you get computers to approximate solutions to equations and all this jazz. Right? But one great thing about Newton's method is that when you get close enough to a true zero, the algorithm exhibits quadratic convergence. What that means is that when you get close enough, all right, that means that with each new iteration, you double the number of decimal places of accuracy. Okay, which means that if we're good to 4 here, we might be good to like 8 decimal places over here, right? And then 16 places for x5 and so forth. So when this works, it can work very well, and we get very rapid convergence towards the 0, to many decimal places. Yeah. Again, this is probably good for like 8 decimal places, not 1. Anyway, question?
I'm talking about the thing you said about the double division. So
No, yeah. So you do this, right?
Yeah.
Some people go all this divided by this times that. That's not right.
okay,
Okay. What if you had 8?
because you come up with the same answer though, if you do it both ways.
Let me give you an example. Okay.
Okay.
Look at this. 8 divided by 2 over 4. Now, of course, this is 8 over 8 or 1. That's correct. Okay. What do a lot of people do though? 8 divided by 2 times 4. This is like an IQ type question. 4 times 4 is 16. That's not right. Basically, in order for this to work, you either need to do a double division, 8 divided by 2 divided by 4, or you group the product. You can group
Okay,
the product.
yeah, that's what I meant. If you
Yeah.
group them on the bottom.
If. But a lot of people don't do that. They just go 8 divided by 2 times 4. You agree that's wrong.
Yeah, that's wrong.
That's wrong.
Yeah.
16 is not 1. Yeah. Here's another thing. I tell my 3-time people this. And in fact, when I was a TA, people love their graphing calculators, but they always mess this up. A lot of people do 2, what do people do? 2 exponent 3 times 4. Is that going to work? No. Because this is 8 times 4. This is 2 to the 12th. Okay? So you have to know your order of operations. All right? So be very careful. You better put grouping symbols here or process that as 12. Otherwise, you're going to do the exponents first. Okay? Just like over here, you really should group this or group this or work this out. Make it 8. Or do a double division. It's 8 divided by 2 divided by 4. That works.
So as long as you multiply together first on the bottom before you
That
do
works.
the day, okay.
But again, on the test, a number of people, it was something like 10 over 27 pi, and they went 10 divided by 27 times pi, and they messed it up. A number of people did that. careful of that. All right. So yes, that's pre-algebra, and yes, some people make mistakes there. Okay, questions? Questions? So, as I said, this section is not that hard. It's that formula. I mean, in fact, in principle, you can even derive it for yourselves. One of my best students of all time, she didn't have good memory, but she was really good at deriving things. She just figured things out. You can figure that out. All right, so that's the key formula there. All right. Well, if you remember it, that's great. Now, I have a question. When does Newton's method fail? When do we see cases of failure? All right. Because, the bisection method, if you can find that, if f is continuous on the interval, f is positive here, negative here, you're guaranteed to have a zero somewhere in there. And you can get some approximation for that, depending on how long you're willing to wait. All right? But sometimes Newton's method, when Newton fails, it can fail massively. All right. When Newton fails, like when animals attack, when Newton fails. And I'm sure Sir Isaac would be very resentful of that notion, but okay. When does Newton's method fail? Let's look at some examples. Let's say this is your x of 1. Okay, you choose that as your c. What's the problem? What's the tangent line up there?
0 there.
Well, the slope 0, horizontal.
Yeah.
Where's the x-intercept for that? There is none. You're stuck. You're stranded up there. Okay. So what choice do you have? You're stuck. Stop. Try new seed. Try new seed. Okay. So again, stop, new seed. All right. What's the problem? F prime at x1 is 0, and that's bad. You're stuck. Okay. That means you need a new seed. Okay. Obviously, the seed that I give you on the test, if I give you this kind of problem, will not do that to you. So be aware that this can happen. And this is a graphical reason why we don't want the derivative to be 0. Again, if f itself is 0, that's great. That means we have an answer, right? So on one hand, you have an answer. On the other hand, you're stuck. All right. That's why f prime's on the bottom. If f is 0, great. But if f prime is 0, you're stuck. All right. Unless you're actually at a 0 right now. Okay. Some other cases. Some other cases. Now this might seem a bit precise, but you can get the general idea. All right. Now, we want a 0, a real 0, right? We want this x-intercept. All right. Now let's say that you kind of guess at it. All right. Let's say you guess here. Okay, x of 1, that's your first guess. Okay, here's your first point. Okay, follow tangent line. You end up here. x2. Take this point. Take his tangent line, let's say it goes like this. What's going to happen? You're just going to alternate between these guys. Bear in mind, it might not be this precise, but you can see how, maybe you're in this neighborhood, then you go to this neighborhood. It may not be these two particular numbers, but basically you're going from this neighborhood to this neighborhood. You might be bouncing back and forth. Okay, it's like an oscillation kind of.
Well, if you were doing that, would you ever come across the horizontal tangent line?
But here's the thing. See, we don't want a horizontal tangent line. We want an x-intercept.
Yeah, but would you stumble across that horizontal tangent line anyways?
Well, it depends. I mean, if it's like this, then you're just alternating, right? But you're right that it might be a case where you get to here and you go, I'm stuck, and then you stop. So basically, you're happy that you're ejecting. And by the way, in numerical analysis, sometimes there are procedures where you're alternating and you go, okay, you know what? If you're alternating, you gotta stop. Stop.
So how do you recognize alternations that you're just going back and forth? Because you're probably not going to go back and forth exactly.
Right, right.
So you're just going to go from left to right.
You know,
left to right.
it depends on the function. And bear in mind, on the exam, I'm not going to pull a stunt like this on you. But I'm just saying, these are things that could happen.
And the sign is a derivative, right?
Well, this is negative. This negative is positive. That indicates you're kind of bouncing, maybe. Yeah, so they're kind of clues. Yeah, yeah. But you don't know. This guy could be really bumpy. You don't know. See, that's the thing. It depends on the function, right? It depends on the function. On the homework, y equals the cube root of x. Okay. Now, folks, just use your basic algebra. What's the only value for x that makes the cube root of x 0? 0, right? X equals 0 is the only 0. Okay, now I hope you know that, right? But still, just for fun, on the homework, I had you experiment with this. Okay? So you should see this on the homework, but I may as well give you a preview. What does the graph of that look like? It's a lazy snake. It goes like this. Now, of course, our sole x-intercept is there. Now, on the homework, I think I offer x of 1 equals 1 as a first guess. You go like this. All right? You have a tangent line. You extend it out. Uh-oh. This tangent line is kind of flat, isn't it? And you're going to get this guy, x of 2. Here's the point over here. Tell me about the tangent line over here. It's very flat, even flatter than this guy. Ooh, oh my. As George Takei would say, oh my. Okay, x of 3. See what's happening here? Okay, you are diverging away from where it should be, right? You're diverging away from the true answer. And by the way, in numerical analysis, there's a general rule of thumb. If the derivative is 0, or even if you're close to 0, that's dangerous. If your tangent line's too flat, you're being thrown way far out. Because remember, tangent lines are supposed to approximate the graph or the function locally, close to the seat, right? The problem with a flat tangent line is that you're potentially being taken far out, where, you know, the graph might be very different. It's like the time machine, right? A million years from now, what's Earth going to be like a million years from now? Will there be an Earth a million years from now? Okay, so, yeah. The thing is, if your tangent lines are flat, you're in danger of being blown out to a really unknown place. Okay, here, again, Newton's method fails massively. Yeah. You're diverging away from the true 0. Okay. So like I said, you know, in our first example, very often, when Newton's method works, it can work beautifully, and you can get great accuracy very quickly. On the other hand, just like sometimes the second derivative test was garbage, sometimes Newton's method just fails, and we got to start again, or we have to use analytic techniques. Maybe the bisection method. Go back to the bisection method. Questions?
Is there because it's too far from 0, or?
Yeah, we're moving away from 0. It's like, you know, we're going boom, boom, boom. We're going to go over here, then over there. We're flying out. We're not converging. We're not converging. Okay? If your iterates are going like, for example, 10, 100, 1,000, a million, that doesn't sound so good. It doesn't sound like they're approaching a nice number. It's like you're looking almost for a limit value almost. Right? Granted, maybe the function doesn't have a 0. Maybe it's indicative of that. Depends. Questions? Questions? That's chapter 4, right? Derivatives, including second derivatives, right? Graphs, opposite graphs, applications, okay? And how we use derivatives to answer fundamental questions.
So this can't tell you if you don't have a 0.
Oh, no, it's not that powerful. Yeah, then you have to know math. Yeah, you have to know math. Yeah, so you can't just use a computer, you have to know math. All right. I mean, we know some things like, if you have a 10th degree polynomial, if you find 10 distinct zeros, you're done.